Okay, let's start talking about how you actually end up implementing these concepts, these multiphysics concepts, into the numerical methods. So this example should be familiar to everybody. This is Fickian diffusion, mass balance. What we have is the rate of change of concentration in a particular volume is equal to the derivative of your diffusion coefficient times your derivative of concentration. What we want to do is make this dimensionally agnostic, which is a fancy way of saying using the vector calculus notation to make it a bit more clear. This is actually more intuitive for me. The first equation here is saying that the rate of change of concentration is proportional to the negative divergence of a flux. So that's a lot of fancy words. All we're saying though is that you have this movement of something. In this case, let's consider it atoms or a flux of a substance, right? And at any given point, the difference between what's coming in and what's coming out is accumulating there. That's it. It's literally in minus out means that you're storing stuff in there. Divergence means to be spreading out. Negative divergence means what's staying in. Now, for that mass flux in this case, that becomes the negative. Well, it's a fancy way of saying that it's proportional to the gradient in some kind of driving force. So in this particular case, a lot of you will be more familiar with saying this is the gradient of concentration. Bear with me there. In my opinion, this should be the chemical potential, and it is generally, but a lot of people simplify that to the concentration, and they end up moving the relevant parameters into your diffusion coefficient. What this heat flux is saying, mass flux is saying, is that you have your rate of movement of material is related to the gradient of your driving force. Okay, so imagine that you're in a car, you're at the top of a hill, and car want to go down the hill, but you're riding the brake. Okay, so you have your gradient of the ground, which is trying to drive you downhill, but you're modulating that through this kinetic coefficient. That's what your diffusion coefficient is. It's the relationship between how much pushing it and how much it's actually moving. Okay, now, what you're going to notice when you compare this to other equations like heat transport, charge transport, this is for ohmic current, we're not into electromagnetics just yet, all these have a very similar form. So for heat balance, what we see here is that the negative divergence of Q, where Q is our heat balance, right? So this is our heat flux, So this is the amount of energy that's coming in versus the amount of energy that's coming out is the amount of energy that's stored. That in particular is called the heat capacity times our rate of change of temperature. Mass we've already covered, that's our second one. And then charge, you might not be familiar with looking at it this way, but this is also another way to frame this problem. I apologize, this should be a lowercase j, but the arrow is covering up the dot there. In this case, our charge flux is related to the gradient in electric potential, times our electrical conductivity. Again, charge in minus charge out means that we are accumulating or not accumulating charges. Okay, so these equations broadly are considered conservation equations because we're conserving a certain amount of things, as opposed to the constitutive contributions, which are the fluxes. Now, when you consider these equations, if we want to build up a mathematical framework for this, how about instead of building one for heat equation, mass equation, charge equation, let's make a general case. And then the difference between these numerically is all coming down to the coefficients that's in front of them. So the difference between heat flux, mass flux, right? Heat flux, mass flux, and charge is just the material property, thermal conductivity, diffusivity, and electrical conductivity. And then we have our driving force on this side too, right? And on the other side, for our conservation equations, we have heat capacity out here. This is basically 1. This is basically 1. Right? So let's generalize this, derive it once, and then just swap out the material properties and the input properties. So this is what COMSOL has done, and this equation looks formidable, and that's because it is, but we can still break it down. So this is the simplified view, if you believe that. Let's go through it piece by piece. Okay, so this is our divergence operator. So everything inside here is our conserved flux, right? Here is our constant, or our material property, not necessarily a constant, times our gradient in a something. It could be related to the property of interest. It could be another expression, whatever we like, but this is called the diffusive term. We also have a convective term, which is also repeated out here. I'll come back to that one in a second, and a source, but all this comes into our conservative flux. For our normal, for mass balance, heat balance, charge balance, this term is what makes it parabolic and what makes it the conservation equation. Okay, the naming convention for this comes out of consideration with mechanics. So generally speaking, the force is proportional to the velocity through the damping coefficient. That's our damping force. Similarly, for this one, this is the acceleration. If we're considering displacement, second derivative of displacement with respect to time is the acceleration. So this would be our mass term, right? F equals ma. Now, these terms here, when we're talking about the convection here versus here, if alpha is not dependent on temperature, not dependent on space, then these two terms are equivalent because it can come out of the divergence. COMSOL will largely take care of the differences between these for you. So you just have to follow through the templates. But there are some key differences, particularly when we talk about the boundary conditions. Finally, we have the source terms. It can either be inside the divergence or it can be outside. And then the absorption, which is dependent on the actual value of your quantity of interest. Okay, so taking this general form, this is called the coefficient form in COMSOL's parlance. What you do is then you swap out and you set some of these parameters and constants to 0, thereby eliminating them from the equation. So what we're going to get is Laplace's equation by setting almost everything to 0. We have Poisson's equation by we keep the source and our coefficient in front there. Right here it is when we have some absorption. Here it is when we have the heat equation. So now we're into parabolic equations. Wave equations, we consider the second time derivative, and convection diffusion equations. Now we have our convective term here. You'll note that it's outside of the divergence operator. So now let's talk about the boundary conditions. There are two types of boundary conditions, Dirichlet and Neumann. The Dirichlet are kind of the most accessible, in my opinion. Basically, what we're doing is we're fixing the quantity of interest at the boundary, or at a point in the geometry. Typically, it's a boundary, hence boundary conditions. We could actually technically put a little point in the middle of our geometry, in the middle of our square, and fix it to there. And there are reasons why you would want to do that we might go into at some point in the future. But the important take home here is that we're actually fixing the quantity of interest at that point. So what we're saying is that, for example, in mass diffusion, concentration is equal to some value at that point. Sometimes you'll see it implemented in software as C is equal to something, or you might see it implemented in something called the residual form, which is defining this function R, which is just C minus C naught. So literally all we've done is a little bit of algebra. We've just moved it onto one side, and then R equals 0 affects that constraint. Please do note that this has implications on the adjoining fluxes. What ends up happening is that the mathematics makes that quantity, that value at that point, in consistency with the fluxes that are going on around that. So that might not make sense to you until you experience it. Maybe a better example for this one is going to be temperature. If you fix the temperature at a point to be a certain temperature, that implies that you're going to be having heat flux coming in and out of your geometry in order to make that the case, right? And sometimes you'll be a little bit confused about that. Just keep that in the back of your mind. Do note that this C naught in this case doesn't have to be a constant. You could have this as an expression. And this is one of the real powers of multiphysics. For example, you could have the temperature being dependent on the concentration of some species. Maybe you're going to say that the concentration is fixed to a solubility, and that solubility limit is related to the temperature. You can put that in directly, and the numerical engine behind it will calculate all that for you. So that's also very useful, but do bear in mind that that has implications on the adjoining fluxes. Also, the last thing I'll mention about the Dirichlet conditions is that it tends to help the problem numerically. Because we're actually fixing the value at a point, it makes the numerics a lot more consistent and a lot more easy to solve. The other type of boundary condition is Neumann condition. These are the two basic boundary conditions, but there are other ones. I'm not sure if we'll get to them in this course or not. For Neumann boundary conditions, instead of specifying the quantity, what we're going to do is adjust the flux and specify, largely speaking, the flux of that material, in particular the conserved flux in this case, at a particular point. So here this would be J is equal to J naught or something of that kind. Where we're going to see this coming in is we're going to see something like inflow or outflow. Now we're adjusting the heat flux. We could do radiative flux. We could do convective flux. We could do mass coming in. We could do mass coming out. Vaporization of anything. Anything that it takes and removes or adds is considered a Neumann condition. More generally, though, this is also going to be expanded to more complicated boundary conditions, like, for example, shear stresses. So for a shear stress, when we get into elasticity, there are normal stresses which are going to come in perpendicular, but we're also going to be able to adjust the conditions which are moving it up and down parallel to that boundary. So that gets a little bit more confusing, but we will get into that, and that's also considered Neumann condition. Here in this case, just touching on that definition of what a conserved flux is. Remember I said I would talk about whether or not these terms are inside the conserved flux or outside of it. That has implications when you're doing the boundary conditions. And it's a little bit insidious if you don't know what you're doing. Frankly, and luckily for you, COMSOL already has that figured out. So if you go to your right-click menus and you select this as inflow, for example, right, then your convection becomes part of the conserved flux, as opposed to putting it in manually, and then you have to be a little bit careful about how you actually put that in. Another video, I'll talk about the weak form, which is actually the numerical form that the finite element method uses, and you'll see a little bit of a difference, but as long as you keep to the tools and the templates built by COMSOL, you shouldn't encounter this.